Good afternoon, everybody. I'm very happy to welcome you all to today's last lecture of the Dasara Lecture Series. This is a new program which we are starting this year. Most of you already know about the activities of the Planetarium. In fact, many of in the audience are all students of REAP, so they already know. So we have activities throughout the year for all age groups, starting from primary school children up to MSCs. And we, as everybody knows, we also have several science popularization activities where general public come and attend our programs. Annually, nearly over 3 lakh people visit our Sky Theatre shows, our Science Park and all. And hundreds of children participate in our workshops we conduct, our REAP program, our science exhibitions, teachers' workshops, in all these. All these programs have been very successful and primarily due to the involvement of the science community of Bangalore. In all our programs, involvement of the science community is immense. They come here and teach. The way Professor Uday Maitra has come here to give a popular lecture. Then in our REAP program, senior scientists from various research institutes come here and teach. And we also take help of these research institutes while we make our new programs, when we design our educational programs and all, and we extensively use libraries of Raman Research Institute, IISc, IIA and all. In fact, this is an institute which is run by scientists. In our governing council, we have 7 very distinguished scientists from various research institutes like ISRO, IISc, ICTS and IUCA. All these years, we were constrained by lack of infrastructure in the planetarium. Like the current lecture is happening in this multi-purpose hall, which was originally meant to be a parking lot. We have converted this into a multi-purpose hall, few labs are there, we have been doing our activities here. On the one hand, the activities are attracting a lot of people. Sometimes for some of the popular lectures, there will not be enough space in this hall. And when we announce workshops for children, sometimes we end up running 4 workshops, though we have announced only for 1. And on the other hand, there are a lot of graduate students who want to do volunteering here. There are many scientists who want to participate and contribute to our activities. And there are many people who want to be interns. All these things we could not do because of lack of infrastructure. But this year, I am very happy to tell you all that Government of Karnataka has sanctioned a building, separate building, an infrastructure facility only for science educational activities. A building is coming up behind this, our existing building, which probably is almost 4 times as large as this. It has 5 lecture halls, an activity room, an observatory, and sky observation deck, and a large auditorium of about 600 seating capacity. This has given a very big boost to all our activities. In fact, it has provided a platform and giving a lot of possibilities to all of us. All of us means to JNP, to the science community, to the students, and also graduates who want to be interns. And we hope to start many new programs in the coming years. Already we have started checking out programs. And one of the program is going to be the Dasara Lecture Series, which we have started this year. When we thought of Dasara Lecture Series, there were several things that had to be done. And most important of them was identifying eminent scientists to come here and give lectures. When we approached Professor Ajit of ICTS, Professor Ranjini Vishwanatha, who is here with us, thank you for coming here, of JNCSR, Professor Nagasuma Chandra, to help us with this, all of them readily agreed. They have given us a lot of time. We had several discussions, and discussions helped us in deciding the number of lectures, the theme, and target audience. We got clarity on all this. I wholeheartedly thank them all for their guidance and help. The lecture, this idea of Dasara lectures was originated when the building, construction of the building started, and then COVID-19 was very rampant. Like all institutions, we also had a lot of financial problems, constraints we had. We approached Infosys Foundation for funding this activity. Srimati Sudhamurthy, chairperson of Infosys Foundation, she readily agreed to fund, and that was a great motivator, and I mean, it really helped us in doing this. I wholeheartedly thank Infosys Foundation for that. We have with us today Professor Uday Maitra to give to tell us about chemistry. The title of the talk is Chemistry is Fun. I thank you for agreeing to come here and give the talk, sir, and I extend a very warm welcome to you. I extend a very warm welcome to many seniors here. Professor Keshav Bulbule is here. Thank you so much for coming here. And I extend welcome to Vishal Vasan, Professor Vishal Vasan, who is here. And welcome to all of you. Okay. Now I request my colleague Madhusudan to introduce the speaker. Thank you.
It's a pleasure to introduce Professor Uday Maitra, who is a well-wisher of the Planetarium, and he is not new to Planetarium. The connection goes back, way back in 1993, when we first conducted the science exhibition here. He was extremely helpful in suggesting very interesting chemistry experiments, and since then, whenever we had a necessity for good chemistry experiments, we have fallen back on him, and he has always been extremely helpful. So it's indeed a great pleasure to introduce a well-wisher of the Planetarium, Dr. Uday Maitra. So he is currently a professor at the Department of Organic Chemistry in Indian Institute of Science, Bangalore. He did his BSc from Presidency College, Kolkata, and MSc from IIT Kanpur. And he received his MPhil and PhD from Columbia University in 1986, working with Professor Ronald Breslow. So following a postdoctoral stay at the University of California at Berkeley with Professor Paul Bartlett, he returned to India after a year at IIT Kanpur and moved to IISc Bangalore in 1989. Incidentally, that's the year Planetarium was set up. So, his research interests are in the chemistry of bile acids, hydrogels, metallohydrogels and organogels, organic inorganic hybrid materials, photoluminescent sensors, etc. His group has recently developed a general strategy for low-cost, paper-based photoluminescent sensors for enzymes and biorelevant small molecules. He is also greatly interested in chemistry education and is a regular participant in a variety of outreach programs for high school and undergraduate students. He has received a number of awards, not surprising, including the S.S. Bhatnagar Award in Chemical Sciences in 2001, and he is an elected fellow of the Indian Academy of Sciences and Indian National Science Academy. And we are extremely honored that you are here in the inaugural Dasara Lecture Series. And I'm sure all of you are waiting with bated breath, seeing all this paraphernalia here, a lot of action going to happen. That's the way to learn chemistry. And the fact that chemistry is fun, as he puts it, is really true. And hopefully a number of you would be willing to take up chemistry as a career very seriously. And we also have two of his students who are helping us in the program today, Arnab and Pankaj. So welcome to you both. And Thanks for coming. And now I request Dr. Uday Maitra to take over.
Thank you very much, Dr. Madhusudan, for the very generous introduction, and also for, shall I just wait to get this one done? Okay. All right. Is the voice level okay? Okay. All right. So I'm very happy to be here today. Thank you very much. And it was very nice to hear from the director about the progress that the Planetarium has made in recent years in getting a new building done, which I think is going to significantly enhance your activities, and more students will be able to join. So this was just for a little bit of fun here. So let me move on to the first one. By the way, do any of you know where this picture was taken? And what is this mountain called? It's a famous mountain in another continent. It's a Table Mountain in South Africa. I was there participating in a chemistry education conference not too long ago. And in fact, we did an event of this kind throughout a day in a science museum. So I'm happy to do this thing in my home. Well, it's not my hometown, so to speak, but then since I have been here since 1989. So we are going to do a demo about chemistry, and the title is Chemistry is Fun. Let me again introduce my two students who are going to help me, Arnab Datta and Pankaj Chaturvedi. They are both PhD students in my group. I forget which year it is, third year or beyond. But I should also mention that both of them are Prime Minister's Research Fellows. So that is a very, very prestigious fellowship, which gives almost double the fellowship amount compared to a normal fellowship. So they have done really well to earn this special honor. Okay, I see slightly older students from high school on this side, and perhaps some very young students, well, including some very young students here. So I will have something for everyone, okay? But those of you who have been studying chemistry as a separate subject, be honest. How many of you dislike chemistry? Okay, that's not surprising, because, you know, if when I look at the curriculum, whether it is SSLC or CBSE or ICSE, 11, 12, standard or first and second PUC, it's terrible. You need to study a lot of stuff. And what is really surprising to me is that the module on chemistry in everyday life comes at the very end of class 12. When the teachers don't have time, they will skip that one because there is no chemistry there. They think there is no chemistry there. That's the last chapter. So I think teachers are not to be blamed. It's the system that promotes and continues with something which is very, very old-fashioned. Okay? And you need to memorize a lot of things. But chemistry really is not like that, because I would like to, things are messed up here, right? What is everywhere? Let's put the letters together. Okay, so I would like to highlight to you that chemistry is everywhere. In fact, chemistry is in places which you may not even know. So I would like to spend a little bit of time talking about it. This is a picture of the Earth. This picture was fondly called the blue marble. It was taken in the last planetary mission to, last manned mission to Moon in 1972. That was Apollo 17. You all know that, you know, a new mission is being planned for, in 3 to 5 years from now. No, it's okay. Let them say whatever they feel like. And then this was a picture of Mars taken in 2006, and you see the difference. There's no water and there's no life. So chemistry makes life possible. And some of you might have already seen that I'm wearing a periodic table tie. Periodic table is basically listing of all the elements that we know as of now, 118. And If there are no atoms, we don't exist. And atoms do not make up do chemistry, because chemistry, to define it very, very simple way, is about making and breaking bonds between atoms. Okay, if there is no breaking or making of bonds, there is no chemistry. And we are alive, I am able to speak, you are able to listen, hopefully, and not sleeping, because chemistry is happening in our body all the time. And as I said, chemistry is everywhere. And this is something that you might have seen about a year and a half ago, right? Mars rover being lowered by a special parachute. And then, if you look at the rover, okay, it carried all these equipments, all right? But most of them actually do chemical analysis of the soil of Mars and also the very rarefied atmosphere. So, while we need good physics, good engineering, good rocket science to take the rover and land it safely on the surface of Mars, and I'll show you one more example, but one of the main reasons it is sent there is to find out the chemistry, because that alone can tell us whether Mars or any other planet ever had life or will be able to support life in case Earth becomes inhabitable. Okay. So one of the major purpose of this planetary mission, in fact, is to do chemistry on other planets. I will show you more example. But as I said, chemistry is everywhere. This is another picture which the younger people in the audience, perhaps they were not born at that time. This was a picture taken on the US Independence Day in 1997, I believe. And yes, July 1997. And you see one of the most expensive remote controlled cars, okay, touching a surface of a rock on Mars. Okay. And again, this equipment costing about 500 million US dollars. It used to be less in rupees at that time. It's much more now. It is actually positioning an equipment against the rock to do a chemical analysis. Okay, I will not go into the details about what this analysis found, but the point is that was one of the major purpose of this job, of this planetary mission. And then fast forward from 97 to 2005, you see the surface of Titan. Okay, this was, some of you may know or heard about this Cassini mission. Cassini went to which planet? Saturn, right. And Saturn has many satellites, including one which is called Titan. Titan, you cannot see anything. It has dense atmosphere of methane. So what Cassini did is to send a probe, small spacecraft called Huygens probe, and this probe went and dived onto the surface of Titan. And before it crash landed, it took these pictures. It is about 15 centimeters. And one of the things it found is that Titan's surface is very cold. There was sea of liquid methane, which boils at minus 180 degrees centigrade. And there was methane clouds and methane rain. So the only difference, or major difference between Earth and the surface of Titan is that we have water ice, water sea, water rain, and there it's methane because it's very cold. Whether that can support a different type of life we cannot even think of, we don't know. Okay. At least that's not life as far as we understand it. But what I would like to point out to you, that this instrument, apart from having all these batteries around it, also has a chemical instrument called GCMS. Most of the children may not know what it is, but that is to analyze the air or the atmosphere of Titan through which it descended. So it carried out a lot of chemical analysis. And not too surprisingly, I also love doing a lot of experiments, and you can see that I'm doing some experiments on Mars. Right? This is a picture of Mars available about a year and a half ago. You don't believe it, right? You don't believe that I have been to Mars? And you see my boarding pass. Okay, I have a boarding pass, but not for my past trip. It's for a future trip in July 2026. So that picture may be possible in 2026. Okay, jokes apart. Actually, you can also get a boarding pass in your name. You go to the NASA website and do all the necessary things. I got it done for some young enthusiastic kids in our institute. Every day. Is anybody's birthday today in the audience? No. So every day, because there are only 365 days in a year, right? Somebody or other must have been born. Okay, and some very interesting, exciting scientific events have taken place. So let's have October 1 and October 2. Tomorrow anyway, we are talking about the weekend, Saturday and Sunday. October 1, somebody named Otto Frisch was born in 1904, and he interpreted nuclear fission with a very distinguished lady, Lise Meitner. Okay, I will show a slide about her, okay, because she has a very special place in the periodic table, not in this one, but the later periodic table. October 2, William Ramsay. Many of you have heard about the noble gases, which are like names? Neon, krypton, xenon, radon, right? So he's the one who discovered, co-discovered many of these noble gases, and he got the Nobel Prize, Noble Gases Nobel Prize in 1904. I'll mention his name once more, okay? And then there is another, he's a chemist. He got Nobel Prize in 1957 for nucleotides and enzymes. This is something the older students would understand. I said Ramsay has some connection with IISc, in fact. The first director of IISc, Maurice Travers, was actually Ramsay's student, and he was, in fact, a co-discoverer of some of the noble gases. This is the picture of Lise Meitner. In fact, many people think that she was unfairly not given the Nobel Prize. She was nominated many, many times, but she never got the Nobel Prize. But then, her name is permanently there in the periodic table, because element number 9 is called Meitnerium, okay, for those of you who may not know. Okay, so the theme of today's, or this Dasara lecture is structures at different scales, and I assume that you mean length scales. So here are some length scale that I would like to discuss with you. We are somewhere over here. 10 to the power 0 is what? 1. So 1 meter. Some of you are about 1 meter, maybe a little more than 1 meter. I am close to 1.8 meter. Okay. So that's where humans stand. And on this side, this is actually what is called a log scale. Okay. It's minus 10, 10, 0, and plus 10, but that's the power. Okay. So the differences are huge. So 10 to the power minus 10 meter is very, very small. 10 to the power 10 meter is very, very large. I will give you a calibration in a minute or so. So this is our scale. And physics, of course, physics deals with everything. Okay. But generally speaking, what you study in school, there, physics deals with some things which are really, really small, subatomic particles, which have this kind of a size, or big planets, planetary systems, okay, Milky Way, and those have dimensions of that order. Just to give you an idea, most of you have heard about light year. What is 1 light year in meters? Light year is actually distance, right? It's not time. So light year is about 1.5 times 10 to the power 15. Okay. And let me test your astronomical knowledge also. What is the distance between the Earth and the Sun? Yes?
1 astronomical unit.
And how many meters is that? Okay. So this is just to give you a scale, that is 1.5 times 10 to the power 11 meters. So that is somewhere around here. Okay, this is just to give you an idea about the length scale. I'm only talking about physics. I'm supposed to give a talk on chemistry, right? Chemistry is right there in this distance. Chemistry, in fact, deals with things which are as small as this or as large as this, along with cooperation from biologists. Biology deals with things which are bigger than atoms, because atoms and molecules are small. And those small molecules, when they join together, they form bigger things, bigger molecules, proteins, carbohydrates, nucleic acids, and us. Okay, so chemistry and biology, they hold their hands together, and then they span this entire distance over here. And of course, physics is there everywhere also. All right. So I will use this thing. Chemistry is cool. So I'm using a cool color for chemistry. And biology is hot. So I'm using a red color there. Okay. Yeah, just going back one step. So we will see some cool chemistry now in the next few minutes. I hope you won't get bored in case I overshoot my time. It's already 4:35. Okay, I'll try not to. It's very important in science, or for that matter, any subject, to ask questions, right? But then, many of you who go or will go to coaching schools, sometimes they will only teach you how to find 3 wrong answers. Okay, not necessary to find what is right. So don't get into that trap. Always try to understand why certain things happen, rather than trying to find out why it would not happen. Okay, so I will give you an example of a very famous person. This person, I will reveal his name in a minute. He said that you remember that, particularly small, those of you who are smaller, go to school. When you come back from school, who is at home? Mother. What does she ask you? What did you do in school? Okay. So this gentleman says his mother never asked him, what did you study? She said, did you ask a good question today? Okay. And then he goes on to say that difference, asking questions, made him become a scientist. And a good scientist. He got the Nobel Prize in 1944 for discovering what perhaps you all will understand as MRI. You have heard about MRI, magnetic resonance imaging. So this MRI's principle was discovered by this gentleman who says his mother encouraged him to ask questions. So all of you should ask questions, okay, including asking questions to me. Even during my presentation, if you ask questions, I'll be more than happy. Okay, so this is a question that I am going to ask you. No, this is not a question I'm going to ask you. It's only an example. All of you know this. Okay? So there's no point asking things that you already know. We should only ask things about which you don't know. What is this then? It looks very similar to this. Okay? And those of you who are very young, who are not yet in high school, may not know what it is, but I will try to explain to those who have been to maybe 11th and 12th standard what this one is. It's actually a chemical reactor for which the builders got a Nobel Prize. Okay? So I'll come back to that. Okay. So you see balloons there, you see balloons here. What are we going to do with it? Why this balloon here? And why is it floating, by the way? Helium, right. It can be helium. Can it be something else? Hydrogen. Right, it can be helium, it can be hydrogen. Both are lighter than air, and therefore they will float. But I want to know whether it is helium or hydrogen. How do I know? All right. Let's see whether we can have a little bit of fun. So Arnab, can you help me with this? But then, doing any chemistry experiment requires taking precautions. Okay? In fact, to the extent that I in fact encourage people who are cooking to wear some sort of a safety goggles. There are many things that can happen, and then Deepavali is Deepavali is around the corner next month sometime, I guess, right? So for bursting crackers, you should always put one of these safety glasses. Those who do not wear glasses, okay? Because eye injury is one of the most common problems during Deepavali. Okay, so safety. Since we are going to create So what happens when hydrogen burns in water, in air? We produce water. Okay, it generates a lot of heat and light, but then we will generate water. Okay, so this is the way to make water. But then we need to be careful. I have done this thing many, many times. As long as the balloon is about 2 liters, which is about this size, and as long as it is about 5 feet away from everybody, it's absolutely safe. And just to be on the safer side, we also have a fire extinguisher kept there and one on that side. Okay. Are we ready? Let's see what happens. Not bad. That was a boom, and I think this one we can put in the same place because this is too close to the screen. So this is also a measure that I use about 5 feet away. And you see there is absolutely no problem. It's just that we do it only once more and that's it. All right. But there will be a question for those who have gone to high school. The size of the balloon is 2 liters. Okay. So I would like to know how much liquid water burning 2 liters of hydrogen gas will produce. How much liquid water comes out of it, whether it can solve Bengaluru's water problem, and how much hydrogen you have to burn. Okay, are we ready? I'm safe, you are safe, Hall is safe. Except, some years ago I did it in an institute in Hyderabad, and they filled a balloon of this size. And when it blew up, there was a pretty much like a shock wave, and the director of the institute was literally, he was shaken. All right, so this is for my online lecture, so I will not show you the video part of it. This is another experiment. See, chemistry often looks like magic. In fact, no, because so much heat was produced, all the water evaporated. So if I had measured the vapor pressure of the room before and after, there will be a very small difference if I can measure it. This was, obviously this is hydrogen. If it were balloon, it will only pop. There will be no flame, no sound, nothing. That's right. So we have also proven by burning it that it is hydrogen.
Can we actually make water from this hydrogen if we do these things in a controlled condition and that temperature can be reduced?
Yeah, so in that case what you need to do is pretty much the way you burn a Bunsen flame. Okay, so you have to have a controlled flow of hydrogen, make a flame. Yeah, make a flame, and then around that you need to keep some sort of a cover which is cooled so that the water vapor can condense. Nothing will happen. Helium will just, the balloon of course will leak, because as soon as I put the flame, the balloon will burn, the rubber will burn and the gas will escape. That's all. Nothing more than that. Yeah, inert gas. But is there any other gas which would be lighter than air? No, which is flammable. Because you said that it can be either hydrogen or helium. I said that there is a third contender which suddenly popped up in my mind and said that, why did you exclude me? Oxygen doesn't burn. It supports combustion. Methane, right. Methane is, molecular weight is 16. Okay, so the relative density is 8. Air is 14.4, so that will also float. Very good. So magic writing is an experiment that I'm going to do first with the help of you and you. Can you please come? Bunny. Okay, this is a very safe experiment, but I want to make sure that you know that even when you are putting the chalk on in your vessel, you need to protect your eyes. So you are looking good. And then you put a glove on her right hand, and what's your name?
Sumeru.
Sumeru. And your? Akshaya and Sumeru are going to help us with this experiment. Boy, you look like a chemist. You put it on your left hand. and right hand. So, if I were a magician, I will only do the magic and not tell you what is the science behind it. Because magicians make use of a lot of physics, a lot of chemistry, not so much biology. And then it appears like magic. So today, certain things we are going to do will appear like magic, but we will explain why it happened like that. So I am going to ask them to hold a banner. Okay? And that banner, again, if I were a magician, I would say nothing, there's nothing written on it. Okay? But then obviously something is written here. So open it up and let him hold at the top. You move it. You hold it with your left hand. Because I'm going to spray something, you hold it here, hold it here. And you hold at the top right side. Okay, so here is magic. Nothing is written there. Okay, but I'm going to spray something, this liquid, this brown liquid. This is safe, the paper is safe, but just to be on the safer side, I wanted them to put on the gloves and wear the safety goggles. Okay, so I'm going to spray this liquid here. Okay, now I'll just just cover your nose. Ideally, you should wear a mask while doing this experiment, but nothing will happen. This is just a simple spray. Okay. So what happened? Is it magic? No, it's all chemistry, right? So one liquid, two colors, and this is only possible because of chemistry. Every color that you see, the one that he is wearing, she is wearing, all these colors are because of certain chemicals. Okay, so Sumeru and Akshaya, right? I got your names right. Thank you very much. Thank you very much. You can go back. And if there is a little bit of a cello tape available, we can stick it here. Thank you for helping us with this experiment. Okay. So now the experiment is done, or the magic has been done, but I need to explain what happened. Okay. So what I'm going to do is to show you the chemical equation that may not be absolutely clear to many of you, but those of you who have studied in 11 and 12 chemistry will be able to understand that the letters which turned blue were written with this chemical, ferrocyanide, and the letters which turned blood red or maroon were written with potassium thiocyanate. Both of them are colorless. And here I have ferric chloride solution, iron chloride. So this is also harmless. Okay. So when I spray, there is the formation of what is called Prussian blue. This was used as a blue pigment in the 18th and 19th centuries. And the other one that is formed, the maroon color is formed between the reaction between iron and thiocyanate. So that's how we make these banners. And if you learn more chemistry, you may be able to generate even more than two colors. Okay, by choosing other chemicals which are colorless to begin with, but with iron, they will turn into different things. Okay, little bit about the periodic table, because 2019, there was a big celebration because the United Nations declared that as the International Year of the Periodic Table. In fact, we had many events in Bangalore. There was one program in Bangalore International Center and throughout the country. So I thought I will say a little bit about the periodic table. And those of you who are interested in chemistry can look up this particular website called isotopesmatter.org. What are isotopes?
An isotope is like a same molecule with the different protons.
Okay. For your age, I will take this definition. It's an atom. It's not a molecule. It's an atom which has the same number of protons but different number of neutrons. Okay. And isotopes are used in various kinds of studies. Most of you are from this region, Bangalore, let's say. Bangalore is situated at a height of about 900 meters. So the amount of hydrogen and deuterium in your dental enamel, okay, will be different from somebody who was born and brought up in Chennai or who is born and brought up in Ladakh. Because when clouds form, our water that we drink has naturally some amount of deuterium, which is the heavier isotope. 1 proton, 2 neutrons. Sorry, 1 proton, 1 neutron. Hydrogen doesn't have neutron, right? So deuterium has a small presence in water, but when clouds form, most of the deuterium, which is heavier, they precipitate, or the rain has more deuterium in the coastal regions than in high altitudes and high latitudes. So therefore, and those signatures are left in our dental enamel, in our nails. If you look at the hydrogen deuterium content in our nail versus somebody from Norway, and some data are available, you will see that you can distinguish these two. So therefore, I cannot, a Norwegian, for example, cannot commit a crime here and say, no, I lived in India. Okay, I was born and brought up in India. Okay, because it is also used, this sort of ratio, analysis are also done in criminal investigations by looking at the isotope ratio. For example, those who grow certain illegal drugs, you can be easily found out whether they have grown in the open field or in a glass house. Okay, by doing this kind of thing. So chemistry that way is very, very powerful. And so are isotopes. So I will not go into these details. So this is one of the very common isotopes that you may have heard about, D2O. We have H2O here. So what is D2O called? Heavy water. Why is it called heavy water? Because it is heavy. Now, is there a way to prove that D2O is heavy water? Suppose I ask you, can I do an experiment in this room? Yes, tell me. I can do what? Wait. Yeah, that of course can be done because it is, density is higher. Density, yes, water is 0.998, density of D2O is 1.1. You are absolutely right. Density of water is, D2O is higher. But then if I measure the density here, there is a balance inside that room. All of you will not be able to see this. Okay. So let's do something different. And you all know ice floats in water, right? So D2 ice will float in D2O. But what about D2 ice and H2O? It may sink and it will sink. Let's do that experiment. Okay, I'll come back to this. So this is the experiment we are going to do. So Pankaj and Arnab have made these two. This is really a very high-tech experiment, as you can see. We are using nothing but 5 ml syringes, disposable syringes. Did you get any tissue paper? And this is what I call a poor man's deep freezer. Okay. Kulfi makers, do you like kulfi? How do they freeze the milk? They don't have refrigerators in the push carts. No dry ice, that's expensive. Even we cannot find dry ice. Salt and ice. That has been the refrigerant. Because if you mix salt with the right amount of ice or ice with the right amount of salt, you get up to minus 18 degrees. It's pretty low. And that's the same temperature in the freezer part of your refrigerator, right? Minus 18. So, did you get D2O, distilled water ice? Or doesn't matter if you didn't, but get me some clean ice, because this is all with salt. This is cold water. How cold? Okay, so what we did is to take water and D2O in these two syringes and freeze them. One is colored orange, one is colored green. Okay, this is colored with food color. but they won't tell me which one is which, right? But we can find out. If one sinks, that must be D2O. If one floats, that must be H2O. So let's try this experiment. So this is again a very high-tech equipment in which we freeze about 3 ml of H2O and 3 ml of D2O. So let's do that experiment. And what I'm also going to do is to make things a little easier for us, is to remove the plunger. So we have 2 little cylinders of H2O and D2O. This is clean ice. Okay. So we are going to make some really cold water. You know why really cold water? I don't know if any of you noticed it, but what's the freezing point of water? 0 degrees. Freezing point of D2O? You have missed it, but let's see. What's the freezing point of D2O? 3.8 degrees. Okay, and that is why we are trying to maintain, oops, I don't want to show this now. I want to maintain the temperature as close to 0 as possible. Okay? Because we work in chemistry labs, we have all these measuring cylinders and so on. So, Pankaj or Arnab, one of you can come and help me with this experiment. And you guys won't tell me, no, which one is which. So let's try with the green. These days people say go green, go organic. So let's go green first. And you hold this one. So I'm going to drop it. If it sinks, it's D2O. If it floats, H2O. Maybe both of them will sink. But D2O is pretty expensive. So I hope you have not wasted money. This is not. Let's see. Hold it here so that everybody can see. Okay, you are tall and so am I. But this one, this is not sharp enough. One second. Yeah, I think this, okay, now I think. Let's do it before it melts. It broke into 2 pieces, but looks like this fellow is not going to stay at the top. This is not. Okay, let's try again. Okay, now you see. This thing nicely sank at the bottom. So it must be D2O. Thank you. And then the other one, orange one. Let's do the orange one. Orange one, of course, is not exciting, right? Anyway, it's not breaking nicely, but then it doesn't matter because it is, since it is floating, it must be H2O. So let me just get this one done a little bit faster. You know, we are doing this in-person demo after a long time. So some of our stuff have become little funny. They're misbehaving a little bit, some of our gadgets. As I say, this is $1 million gadget. So it is not behaving properly today. But let's see if I can make it come out a little bit. Okay, it doesn't matter if it breaks. Okay, it's floating, right? So that is H2O, that is D2O at the bottom. But the reason we are using cold water is because, as I said, that D2O melts at 3.8 degrees, right? And H2O melts at 0 degrees. So this will melt faster. This will melt slower. And that will also confirm that this is indeed D2O. And then we are using a very small piece. What will also happen is, once the D2O starts to melt, it will start to float. Because melted D2O ice will produce D2O, and therefore the remaining part of D2O ice will actually float on that. Okay? If you are careful to view this after a few minutes, you will observe this. So thank you. One great thing about science is that I said that we are doing the experiments after a long time. But once you have done things correctly, a scientifically done experiment can be done anywhere on the planet, and it will give you the same result. And that's why when we do research, we need to make sure that what we do is done with great amount of care and in a scientific manner, so that it can be reproduced by anywhere on the planet or even beyond the planet. Okay, so that's very important in science as compared to perhaps some other subjects. Okay, I cannot but show this one in the context of the periodic table, because one of the things that you need to see is that a smartphone, not just any mobile phone, smartphone has 4 main components: screen, electronics, battery, and casing. And each of them contains a variety of elements of different types. Okay, this particular image you will find from the internet. What I'm also showing here is that these elements which are shown in the pink color are the so-called rare earths, okay, or lanthanides. And they are not available as much as iron, copper, nickel. So at some point we will run out of these. And the battery, which has really made life so much easier for all of us, including this one, has a lithium battery. Okay, those batteries contain not just lithium but also cobalt. But lithium and cobalt are also not very abundant elements. So the scientists are working very hard to find out an alternative using something like sodium. Okay, so the sodium ion battery may become a reality in the next 5 to 10 years. Okay, now a small experiment. This is little more chemistry, if not organic chemistry. Just like we have our hands like this, which look like mirror images, right? Mirror images. But then there is a small difference. They are like mirror images, but they do not superimpose. Right? I can shake with you right hand and right hand, left hand and left hand, left hand, but not right hand and left hand. Okay? That's difficult. And that is because of this mirror relationship. Like socks, you can wear interchange, right and left. Shoes you cannot. Right? So this is a property not only of our hands, our shoes, but also molecules. Okay? It doesn't matter if the younger children have not seen molecular structures, but there are certain molecules. Molecules are made up of atoms connected in a certain way. Some are small, like hydrogen, 2 hydrogen atoms connected together. Some are big, like one of them I'm going to show you. But their mirror images often show very different properties. Okay, and I will show you one of them today. Well, 2 of them. This is, many of you have used orange peels and you have squeezed it. It actually produces an eye irritant. Okay, I won't tell you how some kids use it, but it produces it has this liquid on the left hand side. But these 2 are mirror images, and one is found in orange and the other one is found in turpentine. They're different. They look very similar, right? They look very similar, but then they are actually mirror images, and they are mirror images but not superimposable. So they have different properties, different smell. Properties in the sense they have different smell. Most other properties are same. There is another one which is called carbone, very similar. So they also have different properties. The one on the left hand side smells like pudina. The one on the right hand side smells like shajira. I'm sure that many of you are fond of biryani. The good biryani is always cooked with shajira. Okay, so it got a shajira type smell. But then what we normally do is we say that, okay, this is what, and then class ends there. Okay, but instead of saying seeing is believing, I'll say smelling is believing. All right, so we have some cotton soaked in our carbone, that is the molecule shown on the bottom left. This should smell like pudina. So you can smell one and pass it on to the next person. These are small cotton balls. These are all harmless materials. And this is the S. This bag has this fellow, which will smell like shajira. Okay, either you can smell or you can take one, keep it in your hand. This is the other type. One mirror image is on that row, other image is here. So you can smell it and pass it on, and then we will interchange the bags. Keep a few in the bag. This is a little bit of chemistry that just like our right hand and left hand do not exactly do the same things, but right-handed, left-handed images of molecules also have different properties. Okay, now let us mess things up a little bit. Now you can see, if you look very closely, you can pass it around that the D2O ice is actually floating on D2O now. You have to look very closely because it broke into two pieces. Okay, so we're going to do something with the elephant, okay, but not with the elephant, okay. This is called an elephant toothpaste experiment. In this case, the event is a chemical reaction. Just like we played around with H2O, if H2O has one more oxygen, it's called H2O2, hydrogen peroxide. Sometimes if you get a cut, go to the health center, the nurse will spray a little bit of hydrogen peroxide solution as a disinfectant. I don't know if I have it in my pocket, but some of the brands of hand sanitizers during 2020, 2021 also contain small amount of hydrogen peroxide, 0.1 to 5%. But you know, Arnav actually developed a very nice way to measure hydrogen peroxide concentration, and he found that 2 out of 5 sanitizers did not have any hydrogen peroxide. But that's a different story. So what we are going to do is, hydrogen peroxide has excess oxygen, so we'll try to get that oxygen out, as shown in this reaction. But it doesn't happen just like that. Just like we had the balloon of hydrogen, it's very combustible, but it won't explode on its own, right, until I ignite it. So what we are going to do is, I need a small beaker. What we're going to do is, we're going to add an sodium iodide, which will make this reaction happen, and that's why iodide is called a catalyst. So I'm going to use, can you open this please? And be careful with hydrogen peroxide, because this is strong hydrogen peroxide. This is 30%, not 0.1 to 5% in the hand sanitizer. So let me also keep a few things handy just in case I get some spill. I should ideally wear safety this thing, but maybe not. Okay, so I'll take about 30 milliliters of hydrogen peroxide. And, you know, just to make this thing go a little bit, make it look interesting, I'm not going to use hydrogen peroxide only. I'm going to add some soap in it, so that when the oxygen comes out, it will produce bubbles. It will make it look foamy, and therefore it will come out as a toothpaste. So I'm going to add this liquid soap. It's pretty thick. So this is something we use in the lab. Let me just mix it together. I think this will do. Okay. And you know why we have the tray? Because this reaction is it's not dangerous, because it produces oxygen, which is good for us. And there are too many of us here, you know, so we are actually consuming oxygen. So it's good to put some oxygen back into the atmosphere. So we put this one here. All right, again you see that nothing is happening. And, you know, catalyst, not everything can be catalyzed by everybody. It's only good teacher who can catalyze the fire in a student's mind. Bad teacher won't. Okay. Now in this case, sodium bicarbonate is a bad catalyst. Or it's not a catalyst. If I add sodium bicarbonate, nothing happens. So sodium does nothing, bicarbonate does nothing. I need to have some water, but this is sodium iodide. So I'm going to add, as you can see that these are all very tested, time-tested experiments. I don't really need to measure the quantity. Ideally, one should, for any serious chemistry performance, one should measure the quantities, but these are simple tests where I really do not need to measure very accurately. Of course, I roughly know what I'm using. Like, they say that after you cook your meal, you add salt to taste. So your mother knows exactly how much salt has to be added, right? So similarly, I don't know exactly how much to be added, but I roughly know what is to be added. Okay? So I cannot hold it and do it because the toothpaste will come out. Here comes the toothpaste out. And you can see that beautiful foam. This is only steam, nothing more than that. Okay? It's got a little bit of a smell from the hand wash. Okay, I can smell the whatever has been added here in the hand wash, but you can see that a little bit of steam is still coming out, and it produces a very messy. So this has to be washed carefully. So wear gloves and all that. And this can be, how do you know it is oxygen? Yeah, oxygen supports combustion. Can we have the matchbox? Is it here someplace? Yeah, this doesn't quite work with matchbox, but you will see that when I touch it with the, ideally you should have a piece of wood which is glowing but not with flame. No, this is a bit difficult, but we can try once more. Can you see that it's becoming brighter? Yeah, this is not the best way to do it, but then if it were carbon dioxide, of course it will stop glowing. So this experiment worked reasonably okay. So this is called elephant toothpaste experiment. You will find a lot of videos on it in various places. Little bit about chemistry now. Okay, I will come back to some very exciting experiments, so don't run away, even if you are tired. Let's see, how am I doing? 5:13. Shall I speed up? Okay, it's okay? All right. So chemical bonding, as I said, unless you make atoms combine, there is no chemistry. And it can be, some of you may have seen this picture. Bond is like a handshake. But then if the hands are not of the same size, the bond is physically weak. Of course, it's a mother and a child. Here the physical bonding is weak, but of course the emotional bond is very strong. Okay. But then if the hands are of the same size, then the bond is handshake is strong and the bond is very strong. So if you have atoms of different sizes, like nitrogen is a small atom, iodine is a big atom. If I have a bond between small nitrogen and big iodine, the bond is very weak. On the other hand, bond between carbon and oxygen, carbon and carbon, carbon and fluorine are very strong. This number may not mean anything to you, but you can see this is only 40. This is almost double of that. All right. Now, if one nitrogen, one iodine is a weak, if I have one nitrogen and 3 iodines, that will be a very, very energy-rich molecule, very unstable molecule. So let's see what it can do. So I have Ni3, small nitrogen surrounded by 3 big iodines, and they don't like it. They don't like to stay like that. Okay. So let's see what can happen. Because Deepavali is on the way, let's do something interesting here.
When nitrogen triiodide, the dark-colored solid, is dry, it is very sensitive to touch or any vibration. Simply touching it with a feather causes it to explode or detonate. One detonation causes another to occur. One product of the reaction is violet iodine vapor.
So this Ni3 is so unstable, so shock sensitive. All you need to do is to very carefully touch it with a feather, and then it explodes. Those things require much stronger
Simply touching it with a feather causes it to explode
shock
or
waves.
detonate.
So those
One
are not
detonation causes another to
nitrogen
occur.
triiodide. Nitrogen triiodide, in
One
fact,
product of
you
the
cannot keep for
reaction is
too long.
violet iodine.
Okay, so that's one video, and I'm going to show you another interesting video. Some of you may have heard of a hydrogen bond. If not, then hydrogen bond is, sometimes when you study chemistry, we often don't tell you why you have to study certain principles. Okay, you study about weak bonds, strong bonds, because these sort of things lead to explosives. Something with a very weak bond is potentially an explosive or a fuel for the future. That's why this kind of research is done. Hydrogen bond is very important, not just in chemistry, but also in biology. Water is a liquid, but ammonia is a gas. And it is because water molecules are holding each to other water molecules through what is called a hydrogen bond. So this is typically how hydrogen bond is shown, but I will not go into those details. But all these important molecules in biology, which some of you have read, some of you will read, like proteins and DNA, they hold their shape and structure and properties so that we are what we are because of hydrogen bond. Hydrogen bond is also responsible for water, as I said, water being a liquid. And hydrogen bond is also responsible for ice floating on water. If I ask why ice floats on water, many of you would say it has lower density. But the next question is, why does it have lower density? That is because when water freezes, it forms a diamond-like structure, okay, shown on the right-hand side. And you can see that little animation. You see liquid water, which is very densely packed, but as it starts to freeze, it opens up. So there is more space, and therefore it is lighter. Okay. And many of you have done this experiment. Take a bottle of water, keep it in the freezer. What happens? Plastic bottle gets deformed. Glass bottle will break. But we are going to do something even more exciting. We are going to take a steel container, put water in it, and freeze it at minus 78 degrees. I'm not going to do it here. That's dangerous. Okay? So I'll show you on video. Watch this.
The ice bomb illustrates the fact that the volume of ice is greater than the volume of an equal mass of liquid water. Some cold water is poured into a cast iron bomb, and a threaded plug is screwed into the bomb so that the bomb is tightly sealed.
So you seal this one tightly, so there's no air gap. And this is
The
dry
bomb
ice.
is then placed into a dry ice acetone slush, which is at negative 77 degrees Celsius, and will cause the water inside the bomb to freeze. A wooden box is placed over the top of the bomb and slush bath.
See how much protection has been
It
taken.
takes a short time for the water to freeze. When it does, the bomb explodes. Some of the dry ice acetone slush is blown onto the explosion shield.
And let's see what happens.
Little bits of the cast iron bomb are left. When the water freezes, tremendous pressure is produced. The pressure is enough to cause this cast iron bomb with more than 1/8 inch thick sides to burst.
Okay, so hydrogen bond is important because while freezing water into ice, I'm losing a lot of hydrogen bonds. And that shows up as the explosive force if it is done very, very quickly. This is a very rough, simple explanation, but more or less not very incorrect. But then, you may hear about a lot on carbon dioxide these days. It is what is called global warming and whatnot, right? So it would be nice to be able to convert carbon dioxide back into a fuel. Because no matter which form of fuel we use, carbon in particular, all of them contain carbon other than hydrogen gas. And when you burn, they will produce water and carbon dioxide. And there's no way right now to convert carbon dioxide back into carbon. But I'm going to show you one experiment which actually does that. How many of you have seen dry ice?
Magnesium is placed in a cavity.
This is a block of dry ice. Okay. And do you know why is it called dry ice? Because it is like naphthalene. It is like camphor. It doesn't become liquid when it melts. Well, it doesn't melt. It goes from solid to vapor. So it sublimes. Okay. So this is a block of dry ice. You put some magnesium chips on it and burn
In a
it.
block of dry ice.
And then you ignite.
The magnesium is ignited.
So you're burning a metal. Normally it will burn in air. But now you see what is done.
And covered with another block of dry ice.
So the magnesium is burning, but there is no oxygen. It's between two blocks of dry ice. But see what happens.
Despite the absence of air, the magnesium continues to glow due to its reaction with carbon dioxide. Because of this reaction, carbon dioxide cannot be used to extinguish magnesium fires.
So if there is a magnesium fire, this is absolutely useless. Because if it is carbon dioxide, I don't know if it is carbon dioxide. Yeah, it is carbon dioxide. Magnesium will burn just like what we have seen here.
The reaction products are white magnesium oxide and black carbon.
So what magnesium has actually done is to extract oxygen out of CO2 and convert it back to C. You may say that's a solution to our global warming problem. It's not, because magnesium metal does not occur freely in nature. To make magnesium metal, you have to input that much of energy that you saw coming out. Okay, so it's not going to help us anyway. Okay, nitrogen is also a very strong bond. It's what is called a triple bond. Not one bond, three bonds between them. It's like three hands being shaken with three other hands on the other side. It's a very strong bond. But it can be broken, it is broken, and it actually makes mankind survive. Okay, I'll come back to this. Because remember I asked you a question in the beginning. Okay, I'll skip this part, but this is fun. But before I show anything else, I have this special glass from 2011. 2011 was called the International Year of Chemistry, because that was the year celebrating 100 years of Madame Curie's Chemistry Nobel Prize. Okay, so I'm going to drink some water. This water, that water. Actually, I'm not drinking it, okay? Because this is not, my students said not for drinking. I'm pretending that I'm drinking it. It's not cold, I need some ice. See what's happening? Color changes. Is the water bad, the ice bad, or the glass bad? Let's find out. Let's pour the water out. Let's pour the water out. Water is still colorless. This shows a red color. And let me put my fingers here. What do you see? Because of my fingers, probably at about 37 degrees, okay, they have warmed up and it has become colorless again. So this has some material in it which changes color between 5 and 10 degrees and will make this change the color. But we are going to do a simple experiment with two other, so that is an organic molecule that is molecule containing carbon. But we have something else here. For those of you who would understand the chemistry, we have the chemistry written in the next slide. So this has a silver, mercury, and iodine in it. And this has got copper, mercury, and iodine in it. So what we are going to do is this material, the yellow material, has been painted into a banana shape. And if I heat it to about 50 degrees, it will start turning orange. Right? So now it's really ripe and good to eat, but you have to do it fast because it will become not green but less ripen again. Because this color change is what is called reversible. It goes back to the original color at about 50.7 degrees. So when it's a little cooler, I think I heated it too much. But what is exciting about chemistry is that you change one atom to a different atom and the properties change. So the apple was drawn, well painted, with a very similar material, except it is not copper, but it is silver. It is not silver, but it is copper. So silver goes from yellow to orange, copper goes from red to black, but at a higher temperature. So let's see whether that happens. Okay, I'll leave some black and red together so that you can see. Okay, so the copper salt went from red to black, from ripe to rotten. But the rotten part, it is already going back to the ripe stage. Wouldn't it be nice if rotten apples could go back? That will be nice. So that's where chemistry looks like magic, but then there's no magic here. So why this happens is very well understood. Okay, so but that is a bit advanced topic, so I will not discuss that today. Okay, so I will finish our today's discussion with two more experiments. One is about this picture. What is this picture? What does this show? Sun, it is a setting sun, but it shows two things together. One is why the sky is blue and why the setting sun is red. Right? Sunlight gives a white, more or less white light. But the sky is blue, setting sun is red or orange. Right? So we see both the colors here. So there's a little bit about light. So when light passes through, let's say, any medium can be solid, liquid, or gas. So three things can happen. Light can transmit, goes from this end to that end, like the light is transmitting from there to here. Nothing is happening in between. It can also get scattered. Okay, scattered light is what we see in the sky, because light has VIBGYOR 400 nanometer, which is blue, 700 nanometer, which is red. So when light passes through a dust particles, like the atmosphere, the blue light gets scattered. So what is left over is red. So when we see the sky, we see the scattered light. When we see the setting sun, we see what has not been scattered, because we're looking at the sun. So blue has gone away, and we see that in the sky, and the setting sun is like that. So we are going to do a simple experiment with this. So I'm going to show you all the three phenomena. Then I say only transmission and scattering. What about absorption? Light can get absorbed and can carry out various kinds of transformations. One is a chemical transformation, which is called photochemistry. The other one is a physical transformation. The light can get converted to light of a different wavelength. Okay, and that is called fluorescence, because you see on the roadsides many fluorescent stickers, sometimes you see those. And so I'm going to show you a very simple experiment. Again, this can be done in a glass, drinking water glass. So this is plain water, and here I'm going to do a bit of, let me see if I have brought this one. This is one. I should have a small milk sachet. What happened to that? I thought I brought it. It was in the bag. Or did it just get dropped off? Ah, it's there. Okay, so I'll put a little bit of milk powder, sometimes just a drop of milk, or a little bit of coffee would also help. So I add the milk powder and shake it. Okay, this is, and you see a little bit of cloudiness, so that will scatter the light. And the third one is more interesting. I take this pink highlighter, okay, and just do it like this. Very simple experiment. Water with a drop of milk or tea or coffee, whatever. And here I have this pink highlighter. And then I will use not white light, but light of two different wavelengths, red and green, right? Do you see the path of the light? No, because it is not getting absorbed, it's getting transmitted. Green light, it goes all the way to the bottom, but if the water is really clean, you don't see the path of the light. But here we are going to see scattering, because I've got those milk powder particles. So I put red light. Now you see the path of the light. Correct? Green, you again see the path of the light, because the green light is getting scattered. Okay, since we are seeing it very close, we see no change in the color. Okay, so transmission, scattering, and scattering. But green remains green, red remains red. But then something fantastic happens with this one. First with the red. This ink contains a dye called solvent red 49. The name doesn't matter. Okay, but this is a pink dye. And this is not just the chemical, but since it's a highlighter needs to have something more so that it sticks to the paper. So let's shine the red laser. What happens? Again you see scattering, because it's got some silica or other things which are used as a binder. Scattering. But with red light you don't see any difference, scattering. But with the green light, see something different. What happens? Becomes yellow. So this is called fluorescence. Let's do it side by side. You see only scattering, transmission, scattering, and fluorescence. Color changes, okay? And it changes because of, I will skip that part, because I shine green light into the pink dye. The pink dye absorbs green light and emits in the orange-yellow range. So this is called fluorescence. Light of high energy gets converted to light of lower energy. I will show you that I don't really have to make the solution. If I just put the laser on this cap also has the same chemical. You see the change in color? But then, not all pink colors are the same. It's green, right? and it's yellow. And that's what makes chemistry so exciting. They both appear pink. And you would think that they are made from the same material, same color. But clearly they are not. This has the same material as the ink, whereas this one has something else. What it has, I don't know. But this is not showing any fluorescence at all. You see the green dot as green dot, and here green becomes very clearly yellow. Okay. All right. So that's about light. Simple experiment with light, and this is as long as you have laser pointers of 2 different colors, you can do this experiment, show it to others, but laser pointers are not to be handled without adult supervision, because these lasers are low energy lasers, but they can damage your eyes permanently. So never looked at a laser directly, okay, and always point it away from everybody else. Okay, this was during my online sessions, but I'm going to show you another simple experiment on fluorescence. Using things that are here on the table. I'm pouring this water here. Okay. So I'm going to put, this is what is called Indian tonic water. Okay. This is used to make various kinds of drinks and cocktails, but we will not get into that because most of those present here are below 21 years of age. But it's called tonic water because when the British came to India and Southeast Asia centuries ago, they did not like malaria. Nobody likes malaria, right? So what they did is that in water they added small bit of quinine, which was known to have anti-malarial properties. But quinine makes the water bitter. So that's why they started making this water into more exotic drinks. But then this does contain quinine, and this is just plain soda you can buy, kidneyless soda. Okay, so let's open this bottle and pour some soda here. This doesn't have quinine. Can I have the lights off, please? But this soda, this Indian tonic water, I'm going to waste 1 can, but that's okay. It's all for the sake of science. This has quinine. Let me make sure I have exactly the same volume. Yeah. They both look similar. Okay? If I taste it, I will figure out that one is slightly bitter, the other one is not. But quinine has a very peculiar property. It shows fluorescence. So that's why I have this interesting. Can we have all the lights off, please? Because we are going to generate light. That one also, or turn the other way. Yeah, that's good enough. So I shine this UV lamp on soda water, and you don't see any fluorescence, okay? You see only reflection. Thank you very much. All right? But this is tonic water, and you can see, even from a distance, you see some difference. And now when I bring the light here, you see the beautiful blue fluorescence of quinine, okay, from tonic water. I put it on the top, put it on the side, put it on the bottom. My lamp is a little too weak, but this is in fact, the quinine fluorescence is something that actually led to understanding and study of fluorescence by scientists. And you see, if I do the same thing with just plain water or carbonated water, also known as soda here, it shows no fluorescence. So this is again beautiful chemistry that can be used to distinguish between things which are otherwise very similar. And let's get some light back on. Yeah. No, there is no reaction. That's true. Yeah, you are right. You are right. So this is also called photophysical science. So you can say chemistry. You can say it's not chemistry. But what is important here is that frankly, nature does not care whether we are talking about chemistry or physics or biology. Nature is nature. And we are only trying to, scientists are only trying to understand nature, right? For our own convenience, for our own limited knowledge, we have separated it so that I don't need to learn all subject areas. I need to focus on only one. No, no, no. There is absolutely no chemical changes either in the liquid or in the property of quinine because it absorbs light and then emits light. It doesn't change. Okay, so that's why you see that I have kind of sanitized this slide to make it sure that I can show this one, and you can see here on the photo of this quinine showing beautiful fluorescence. Okay, the last item of the day. I'm sorry that I'm taking a little longer time, but I hope. Shall I stop? Are you sure? Yes. Sure? All of you agree? Because I keep the last experiment as the most exciting experiment. So we need to turn the lights off again because this is an experiment where we will create light just like what the firefly does. Firefly converts chemical energy into light energy. Okay, but since firefly is a biological species, we say bioluminescence. But the general term is called chemiluminescence. There's a little bit of chemistry I will show for the high school students, little bit. Others may simply ignore it. But this is what happens. How do we generate light? In the good old days when electricity was cheap, we would use tungsten lamps, right? A filament of tungsten will get electrically heated, so hot that it will emit light. Just as what you see in if you heat a block of coal. Otherwise, nowadays we have LEDs where it's called electroluminescence. Electrical energy is converted to light. But chemical energy can also be directly converted to light. And that's what chemiluminescence is all about. So let me show you the science part of it. Here again, we are going to use hydrogen peroxide as our fuel. Because that has got, as I said, extra punch in it. Okay? An OO bond, which is a weak bond. So without going into the details, let me just simply show you. We are going to use 4 types of molecules. Just like quinine shows fluorescence, or quinine showed fluorescence, we'll use these 4 chemicals, which are also fluorescent molecules, and they will produce 4 different colors. So I'm going to use, from your left, Arnab, I may need one more dropper. I will put a little bit of diphenyl anthracene here. Again, it doesn't matter if you don't know the chemical structures. The second one, we will put what is called rubrene, which is a red powder. Third one, I'll put perylene. Incidentally, perylene, which is shown in the sky blue color or the cyan color, some perylene-like molecules are used in the beautiful red cars that look very attractive, right? So those are all perylene-like molecules. So the third one has perylene. And the fourth one, for those of you who have studied a little bit of chemistry, it looks like 2 naphthalenes stitched together. So it is also called tetracene or naphthacene. That's actually, it's so easy, you know, naphthalene balls you can buy for almost a throwaway price. But to put 2 naphthalenes chemically bonded together costs a lot of money. So this little vials will probably cost about 4,000 or 5,000 rupees. Okay? But I would like to thank Merck because they provide some of these materials free to me so that I can share this excitement of chemistry with you. So big thank you to Merck and Mark Sigma Aldrich for sharing these materials with me. Okay. So now I'm going to add a solvent tissue paper. Okay, just to dissolve the dye. Yeah, this we should have 125 ml flasks for this. 1, 2, 3, and 4. Okay, I'll do 2 at a time because I guess I have only 2 hands. Thank you so much. And I'm adding a little more solvent here just for a purpose. Okay, are we ready? Right, these 4 are ready, so I will do these 2 first and these 2 later. But then there's too much light from the screen, so let me put it B. Okay, but I must see what I'm doing, right? So I will add this other chemical called oxalyl chloride, which is not a very friendly chemical, but we are using a dilute sample of that. Okay, I put it there. I put it here. There is a small change in the color that tells me that this material is good. Okay. Yeah, I lost the stopper. No, it's okay. I got it. Now the fuel. Are we ready? So this was for oxalyl chloride. This is for hydrogen peroxide. Okay? Now this will definitely look like a magic. Okay. So you can see beautiful blue color, and it's ice cold. Okay. So there is absolutely no heat in it. It's very, very cold. Okay. And I'm going to do something even more exciting if it works. It may or may not work, but what I'm going to do is to add a little bit of this orange color into the blue. Okay. This will be orange and then white and then blue again. Right? Let's do it again if it works. Orange, white, blue. You know, why does it turn white? Because orange and blue are complementary colors. Those of you who have studied colors would know that orange and blue are complementary colors, and when you mix them in the right proportion, you get white. So that's what we observe. But the orange color, for reasons that I cannot explain right now, orange becomes deactivated much faster. So if I put the blue here, again, we will see the same thing happen. Okay, so the orange is now gone. Okay, so you saw 2 exciting chemiluminescence experiments, and I'm going to do it with the other 2. And this blue color remains for a much longer time. So I'm going to make a different shade of blue and a shade of green here. Okay. So this will give us a sky blue color. And this will give me a green color. Okay, so you can see that beautiful sky blue. And this blue is different from this blue, right? And this color is again, very, very different because we are using different chemicals for each of them. And this, I'm glad that you liked it. And this color will stay for a much longer time. Okay? And you can even see who is speaking. That generates enough light to, so that you can see my face. And if the room is absolutely dark, it looks even more stunning. But you can see that this orange is already gone. Blue is, green is going. This blue is still there with little orange flakes on it. Whereas this blue, or the cyan color, will remain for a much longer time. I think I have taken much more time than what I really needed. These are some other experiments. Now, I'll just stop here. Yeah. Okay, I will do that. But before that, let me ask you, if any of you know, I said this is a reactor which is very helpful for mankind. This is ammonia reactor. Okay, it makes ammonia from nitrogen. And it is used in every fertilizer plant you can think of, including many in India. In Bengaluru, we have a RCF. I think it was called RCF. I don't know what the current name is. But they make a lot of urea. And for making urea, you need carbon dioxide and ammonia. So the ammonia is made from nitrogen and hydrogen. This is a reactor that was made by Haber and Bosch. Those of you who have gone to school would know it's called Haber-Bosch process. They both got the Nobel Prize. And this is a reactor that was made by them, and it is kept in outside a BASF factory. BASF is the world's largest chemical factory. It's like a city factory, or a factory city, in a place called Ludwigshafen in Germany. And this particular reactor was used for 55 years and generated about 800 metric tons of ammonia, close to 1 million tons of ammonia during its lifetime. Yeah, I just want to end. Yeah, before I end, I will go back to the chemistry part of it. Yeah, so what happens here, for those of you who would like to know the chemistry, is that the oxalyl chloride and hydrogen peroxide forms this kind of an intermediate, which breaks down into 2 carbon dioxide molecules. But all the extra energy, because it's a small ring, it has got a weak OO bond, so that all the extra energy stays with one of the carbon dioxides and make the carbon dioxide electronically excited. So you are chemically exciting a molecule in its higher electronic state, but if left without anything else, it will only lose the energy as heat, which is not interesting. Chemical energy to heat, there are other ways of doing it. But in the presence of these acceptors, the acceptor or the fluorescent molecule gets electronically excited, and depending upon the energy level in the acceptor molecule, like the 4 we had here, they showed energy of different lights, okay, or radiation of different colors, because the energy levels are different. Okay, coming back to the elephant. I think the elephant wanted to reappear once more. You know, periodic table has been drawn and shaped into many ways, but one of the things that a mathematician, a Harvard University mathematician, way back in 1950s, what he did is to compose a song from all the elements known at that time. So it became popularly known as the periodic table song. Okay, so I will show you one version which shows some animation. There is also a song by Tom Lehrer himself, but I will not play that today. So let me show you this one. Let me play this song, and if you want, the children can dance.
There's yttrium, ytterbium, actinium, rubidium, and boron, gadolinium, niobium, iridium, and strontium, and silicon, and silver, and samarium, and bismuth, bromine, lithium, beryllium, and barium. There's holmium, and helium, and hafnium, and erbium, and phosphorus, and francium, and fluorine, and terbium, and manganese, and mercurium, molybdenum, magnesium, dysprosium, and scandium, and cerium, and cesium, and lead, praseodymium, and platinum, plutonium, palladium, promethium, potassium, polonium, and tantalum, technetium, titanium, tellurium, and cadmium, and calcium, and chromium, and curium. There's sulfur, californium, and fermium, berkelium, and also mendelevium, einsteinium, nobelium, and argon, krypton, neon, radon, xenon, zinc, and rhodium, and chlorine, carbon, cobalt, copper, tungsten, tin, and sodium. These are the only ones of which the news has come to Harvard. And there may be many others, but they haven't been discovered.
And of course, it goes up to 118. That was probably done sometime in 2015 or something. Okay, so with this, I conclude my lecture for today. I'm sorry that I have taken too long time, but I hope you liked some of the experiments. And thank you. Thank you very much. And I hope that in a little way, I have been able to change your perception of chemistry. So next time you see a product in the market, please read the label and see what are the chemical constituents and how they are going to affect you. So thank you very much again, Dr. Madhusudana, and you for the invitation. Thank you. To dissolve dichloromethane, methylene chloride. Yeah. Yeah.
Reactions that happen when you combine lemon with ginger and other.
Yeah, some of these are much more complex because what I showed are with the pure chemicals, but then certain things are observable even in our daily life. For example, if you take turmeric powder, ginger and lemon, I would not be able to tell exactly what may happen. But if you take, for example, haldi and let's say baking soda, this is some experiment even the young children can do. What happens? It's an indicator, the color will change. I think the allyl chloride is smelling. So it's an indicator. Well, actually, the indicator is a chemical compound called curcumin. And there are some studies nowadays that this curcumin in haldi is a wonder drug or nutraceutical, as they can say. It apparently protects us from many diseases. Okay, it's not confirmed, but that's the belief is. But the point is that in the presence of a base, it changes color. And in certain regions of the country, if you have a swelling in your hand or leg or someplace, they will mix calcium hydroxide, what is used in making pan, one of the ingredients, calcium hydroxide, lime, and haldi, and make it warm and put it on the swelled part. And apparently it becomes normal after some time. But then the point is, once you mix lime with curcumin, it becomes a blood red color. Okay, it changes color. So yes, chemistry does happen. For example, another thing that is often done is that those of you who perhaps eat fish, you know that there's something called a fishy smell. Okay, those who like fish, they may not object to that, but for many others, it's a pretty offensive smell because these smells come from various kinds of amines, organic amines. But the reason is that the fun part is that you are adding lemon juice, which will neutralize the amines, they will protonate the amines, and make it so-called ammonium salt. And as a result, you are actually doing a titration by adding lime to, let's say, a fish, and all the smell will go away, simply because you are converting a volatile, offensive-smelling amine into something that is non-volatile and water-soluble. So we make use of chemistry every day in the kitchen. And there is a rich chemistry that is known. Some of it is pretty complex because, most of the natural substances that we are using are not single components. They have multiple components, many things. But something that is very informative is that if you take any packaged bread, it will have at least between 6 to 10 externally added chemicals. And these will all have some 3-digit number with a preceded by an E. It will have something like E540. And these are all, or it will also say INS 540. So these are approved food additives which are used for certain kinds of function. Just like sodium bicarbonate that I mentioned, we use it for baking purpose, but commercial bread will contain many things apart from simple sodium bicarbonate and yeast. And you can learn a great deal of chemistry by simply Googling those various components with the E numbers. And if you go back and see if you have a loaf of commercial bread and look at the package, you will be amazed to see how much of chemistry is involved in making a simple loaf of bread that we buy for 30, 40 rupees. I hope I have answered your question partly. So children, one interesting project you can do, you take toothpaste of different types. Sensitive toothpaste with fluoride, other types of toothpaste, gel toothpaste, and look at the composition. And list them, and you can find out what are the differences. Most of them are very similar, but there will be some very key differences in the fluoride content, in having some other materials, this or that, from here and there. So it's very interesting to try to connect chemistry with our daily life. So I didn't make a big effort to do that because I wanted to show you something which is more exciting, entertaining, at the same time educative, I hope. And I hope that young and not so young, everybody liked the experiments. But if any of you would like to have any further correspondence on anything else that you might have missed out today, I will just add my email address here. You can also Google and get this information, but I'll just put my email address here. Oops. Let me make it a little bigger. Oops. IN. Yeah. So that's my email address. So in case any of you have a question, please feel free to send an email, and in the subject line you add Planetarium event so that I can connect the question to this evening's discussion. Yeah. Yes, absolutely. Absolutely. I think the way we learn things, the way the curriculum is set up, it doesn't make it look very interesting in many cases. Chemistry definitely, other subjects also. Physics somehow, physics, I think the students can relate to things which are either too small or too big, which we see every day. But chemistry is responsible for everything that we do every day, starting from the toothpaste that I mentioned. But somehow we take it for granted and not really pay much attention. But biochemistry can also be very, very colorful. But there are, for example, all these beautiful flowers that we see all around us, and many natural products which are very exciting. So that can be as exciting as chemistry that I showed. For example, this fluorescence that I mentioned, there's a very interesting, important fluorescent protein that is found in certain organisms called GFP, green fluorescent protein, and that led to a lot of discovery about fluorescent proteins found in other organisms and many different colors. So yes, there is color in fluorescent proteins and fluorescence in those proteins. Yeah. Yeah, you simply have to add sodium bicarbonate or baking soda. If you want, suppose somebody has added lemon juice to fish, which was smelling bad, you can again bring the smell back by adding baking soda. I don't know if you want to do it, but yes, because this is like adding a proton or removing a proton. So you can add acid, like lemon juice, or you can add a base to remove the proton. Pardon me? Oh, this is absolutely reversible, and it's very simple. I mean, these acid-base reactions are one of the simplest reactions, extremely rapid. So you can take, for example, if you have, for instance, if you have an acid spill, suppose I have a bottle of hydrochloric acid and it spills and it smells a lot. All I need to do is to pour a lot of soda, baking soda. Okay, it will produce a lot of carbon dioxide, but it will neutralize it. So it can be done, and for many spills, this is how you do it. This is how you handle it. Similarly, if you have a spill of sodium hydroxide, okay, very strong alkali, and then the way to do it, handle it, is to add something which is acidic, but not HCl, because one devil you are trying to add one more devil, so you add acetic acid in that case. So you add vinegar. So vinegar and sodium bicarbonate are used in cooking because one is mild acid, one is mild base. But you don't go to something like as strong as hydrochloric acid or as strong a base as sodium hydroxide. So those are the extremes, but we play somewhere in the middle. I hope I have answered your question. Thank you.
Sir, this is a question asked by an online participant.
Yeah.
His name is Pramod Keshav.
Yeah.
He asked, where can we get heavy water to perform any experiment?
Okay, you cannot. Unless you are in a research laboratory, you cannot, because even for getting this free heavy water from Merck, I had to fill up several forms because it's a restricted material. It shouldn't be, because deuterium is present in our body as well in a small concentration, but it is used in nuclear reactors. So those who manufacture D2 or any deuterium containing material, they won't sell it openly, but so unless you are associated with an academic research laboratory, you cannot buy D2O off the shelf easily. Well, not easily, I mean you cannot buy D2 off the shelf.
The second question that he has is, can you suggest some books on chemistry experiments?
Okay, depends upon the level of experiments, because one can take a look at the web site and search for kitchen chemistry experiments. For those of you who are very young, you can certainly do kitchen chemistry experiments. The same the elephant toothpaste experiment that I did, something similar can be done by mixing vinegar and soap together and adding baking soda, or mixing baking soda with soap and adding vinegar. Yeast, of course, yes, you are right, yeast will also produce carbon dioxide upon fermentation, but that's a slow process, whereas here it's an acid-base reaction, vinegar and baking soda, that produces carbon dioxide directly, and to make it look like a foam, you can add some soap. Similarly, you can also find out that different colored flowers that are produced in your garden. Okay, you can take those flowers and stick them on a tissue paper and add lemon juice or baking soda and see how the color changes. That's again about how acids or bases affect color. And they do affect color, because sometimes there are flowers, I don't have the exact name, I don't remember the exact name, but there are flowers which have the same chemical, but they appear different because the pH or the acidity in the flower are different from one type of flower to another type of flower. So those chemicals, collectively called anthocyanins, they show very sensitive change in the color based on the acidity or basicity. So yes, you can do some fun experiments we're using your flowers in the garden. Yes, if the color changes because of it, because the color would change because of its, because of a certain, even if it is reversible, certain transformation into another structure. Sometimes a closed form of a molecule gets opened up, and that's why it causes a change in the color, because the way the electrons are organized when a molecule is flat is not the same when it opens up. So it can open up because of acid or base, it can open up because of some other stimuli, but then you can bring it back to the original color. But certain properties like light absorbing properties, they would definitely change, and that is what is responsible for the color change.
Thank and congratulate Dr. Maitra for having spent so much of time. A lot of thought process has to go in to demonstrate each and every experiment. Since I am in the same field, I know what amount of the thought process will be continuously lingering. So on behalf of everyone, as a student of science and as a faculty member of prestigious college in Bengaluru city for 37 years. Even I have a mobile lab, but few experiments, especially somebody asked, where can we get the DTO, that is heavy water. In fact, I wanted to ask that question, and you have rightly answered it. I thank the director of Planetarium for having organized so wonderful, enjoyable, because normally we say seeing is believing, not vice versa. Sir said smelling is also believing. A wonderful structure, the mirror images which cannot be superimposed, but they will have totally different properties, like diphenyl. Diphenyl is a very pleasant peppermint smelling, whereas the reverse of it, naphthalene, is cockroach repeller. So I profusely thank you for having spent so much of time. I thank your assistants also. I thank Dr. Matsudan, who invited me today, because though I was not well, looking at Sir's presentation and the organization, the efforts that have been made, especially for coinciding the Dasara festivities, I thank every one of you for having organized so beautifully.
Thank you very much. Beautifully. Thank you.
So I thank Professor Keshav Bulbule for making my job easier. So thank you. Dr. Uday Maitra, we must say that this was really a spellbinding program. We started this Dasara Lecture Series on day one with the cosmological structures. The theme of the Dasara Lecture Series this year was structures at different length scales. So we started with cosmological length scales, the largest that one can think of or get in the universe. And we are ending with all the things that happen at the other end of the length scale, namely the atoms and molecules. So it's a befitting end to the first edition of Dasara Lecture Series. So thank you very much for being part of this. And all the demonstrations, they were mesmerizing.
Thank you.
And what is important is, you have been the perfect salesperson for chemistry today. And if anybody had some kind of a doubt whether chemistry is really fun and whether the title was a misnomer, I think after seeing your demonstrations and the lively discussions that you had, everybody is convinced that chemistry is definitely a subject that should be taken up very seriously. And many of our students here, they are with a PCM background, physics, chemistry and mathematics.
Sure.
So many of them study physics and mathematics, and they generally ignore chemistry, which I hope they will not do after especially this program, because chemistry is the one which bridges physics and biology and all other sciences together. So thank you very much, sir.
Thank
and
you.
as a token of our appreciation, we have a memento, and I request our director to hand over the mementos to you.
Thank you very much.
And we also thank the two students of yours who helped us immensely with the demonstrations, Arnab and Pankaj. So we have a memento for you. So after much food for thought, now we will have some snacks which have been arranged outside. Please join us. And thank you very much for turning out in big numbers today. We were a bit disappointed over the last 2-3 days. You more than made up by this big turnout. So we look forward to this kind of attendance in coming programs. So
Yeah.
thank you very much. And please join us for tea and snacks outside.